Generally speaking, the review is set up to be all free response, just to get us kind of thinking about how we might answer questions, given multiple options. The actual exam will have some multiple choice that are more or less similar to the quizzes that you've been taking. So in some of like the quiz questions, I gave you guys a table that has data in it, and then you can copy and paste that table into Excel and then work your calculations in Excel based on the questions that I give you in the quiz, right? So multiple choice questions might be formatted similar to that. Multiple choice questions could be related to terminology, which I have as a free response practice in here, just because there is flexibility in the answers that you could stick in. But I would say 80% of the test is going to be where you're typing in like a value that you've calculated, or you might be interpreting what a p-value means from a Shapiro-Wilk test, or you'd be writing what the null hypothesis is for like the confidence interval for a true population mean or whatever, right? So most of it's going to be free response. That could also include identifying variables or classifying types of data. So just be prepared to type stuff. But yeah, with that being said, we can start on this. And so I'll give you guys formulas. They'll look like this. You have what each formula is in your notes, so you can feel free to use your notes. Example being like this would be the formula for an exact percentile, or this would be the formula for a z-score. Okay, so you can fill in what those are. You have them prior to the exam. Same thing goes with the word bank. You have that prior to the exam. So you kind of know which terminology you should focus on, or as far as definitions or applications of definitions go. But those things should already be posted on Moodle, or not Moodle. That's my learning management system. They should be posted on Beachboard already. They also should be a part of the study guide that's posted as well. So if those aren't there, and I need to update those documents, and let me know. But I posted them over the summer, so I feel like they should be correct. I haven't finalized the questions yet, but usually it's around 30, like 20 to 30. So yeah, I usually try to make it 20 to 30 questions, and usually it's out of like 60 points. That way you can miss more points, but not do bad, if that makes sense. Yeah. You are able to skip between questions, yes. For people watching the recording, this is for later. But I'm reading messages in the chat, so you are able to skip between questions. It'll be similar to the quiz setup. So if you have like a scenario or a set of data that goes with a particular set of questions, that data will stay with that section. So, and the questions in that section will be in the same order as they would be for anyone else in the class. But you should be able to scroll through the entire exam in one fell swoop. Yeah. Okay. I'm going to close the chat. Oh, just kidding. Well, we need to submit any work. No, you don't need to submit any work. But it's helpful on some of the questions. I will put like show work for like potential partial credit. So an example would be if you're calculating a confidence interval. If you use the correct formula where you're, like this is my mean plus or minus my standard error of the mean times the z-score, and you type out that's your work process, but maybe you use the wrong z-score, I can still give you partial credit for using the right formula, and then just put in your feedback on your exam like, oh, you used the wrong z-score. So That's kind of like the only work that you would be inputting. The free response areas will allow you to type as much as you want to. So, I mean, that's not to say like go type a paragraph of justifications, but um, as far as like you won't be making any graphs, you'll need to know how to read a graph, but you don't have to generate them because I can't. There's no way in the quiz setup on Beachboard for me to ask you to like copy and paste a graph. It doesn't work. So know how to read graphs, but you don't have to make them. Um, as far as work goes, you can type out your plug and chug in your formulas, but that's about it. It's not required. But yeah, okay. That was a long-winded answer. I'm sorry. Okay. Um, other questions before we get started?
Yeah, I have a question. So let's say if we had to calculate confidence interval and you said it involved mean, standard error, and z-score,
Huh?
do we also have to show the calculations on how we got the standard error and also like how we for that like specific calculation?
Um, if you wanted to,
Okay. Will points be deducted if we don't provide it?
no. Usually
Okay.
if I just ask you like what's the confidence interval, I'm only looking for the confidence interval as like the graded answer.
Okay,
The
gotcha.
work before that is just like if I give you partial credit because oh like I can see you calculated the standard error of the mean incorrectly, then the point deduction is less than if you didn't submit any work at all. But
Okay.
that's considering that you use the correct formula because I know like later in the semester we'll be calculating confidence intervals for other things, and a lot of times like people get um like what goes into the actual formula, they get them mixed up. So I'm like, if you use the right formula, then and it's just like a number is off in the formula, I can still give you partial credit. But if you use the wrong formula entirely, that then it's just like 0 points. Yeah.
Gotcha. And does that also go for the same thing in terms of the activity as well? Like the same sort of what you were just saying?
Yeah.
Okay.
Yeah. I think that's why most of the questions I asked you to show your work. That way I can give you partial credit if you get to the like if you come to the wrong value at the end.
Gotcha. Okay. Thank you.
Uh-huh. Okay. Okay, so let's go through the terminology section just as a quick review of some of the words that we've introduced. This is not an exhaustive list of the terminology, I don't think, but these are kind of the more important ones. Um, so let's use the chat. I think that might be the most effective way to go about answering these. So just type what you think the answer is. Any of the words are going to be coming directly from the word bank. So you might have to change how they're formatted. So versus like if something's past tense versus present tense, I don't know. Might not be the exact word, but you're going for something close to. Okay. So number one, finding an individual's percentile for a 1 RM squat is a way to blank them. We're all on the right page, so that's good. The correct answer to this one would be evaluate. So I'm going to change, actually, I'm going to expand this a little bit. And I'll do bold. So evaluate is the answer I was looking for. Reason being is that if some of you put test as well, and this is a great way to segue into a conversation about the difference between measurement, test, and evaluation. Right, so measurement is the actual variable you're collecting. It has a unit to it, right? So like force, time, weight, height, that type of thing. Okay, in this case, 1 RM squat, our measurement might be percent body weight. The test that we use to collect that measurement is the protocol or a piece of equipment, right? So maybe our 1 RM squat, maybe we have a certain protocol that builds a person up to their 1 rep max. That would be considered the test and can vary based on your methodology, but let's just say that's what it is for our example. Evaluation is how we assign worth to our measurement. So assigning a percentile, right, is a way to evaluate a raw score amongst a sample, perhaps. We could do statistics and say, this is how, or if we're evaluating a sample, maybe we can say this is the mean of our sample. We have evaluated our sample in that respect by taking the average of the scores. Okay, so evaluate is a way we assign worth. I don't know, what's another way I could say that? You put it in perspective to the target population, maybe is another way you could explain that. But evaluate would be the answer there. Okay. Questions on that one?
Nope, thank you.
Cool. I've got the participant list brought up right now since we're not doing any data stuff. So if you guys put like thumbs up or anything, I'll be able to see it. But I appreciate the shout out. Okay, number 2, body composition is a type of blank, while hydrostatic weighing, bioelectrical impedance, and skin folds are different blanks to quantify body composition. Okay. Seeing a pretty unanimous thing going so far, which is good because that's what we just talked about. What they said, yeah. Okay, so body composition would be our measurement. And then hydrostatic weighing, bioelectrical impedance, or skin folds, taking skin folds are different ways that we can test, right? Those are different protocols, different methods, different pieces of equipment that could be used to actually obtain body composition. Okay, cool. Number 3, inexperienced undergrads aren't likely to be as blank as graduate students when it comes to marker placement. There's 2 possible answers for this one. So, well, 2 more correct answers, but I'll leave it there. Also, I just realized it's really dark. So as you put your answers in the chat, I'm gonna turn the lights on. Yeah, reliable. That was the one I was going for. But some people might argue that the other answer is valid. Okay, so generally speaking, if you've got someone who's not familiar with a procedure, there's going to be more error or less consistency for marker placement. That's like if they're finding a bony landmark and they're not used to palpating, like say the acromion process, right? If they're not used to palpating that, there's going to be a larger kind of bubble of where that marker placement could be. Therefore, it's inconsistent or not reliable. Some people might also argue that valid is another correct answer because validity has to do with the accuracy of the measurement. So they are less accurate as well, but reliable is kind of like the better one of the 2. For the exam, usually I have a lot of leeway with the differences between reliability, validity, and objectivity, just because each of them has quite a bit of crossover. And I think we talked about that in the first lecture too. So I usually grade those pretty loosely on the exam. But yeah. Okay, number 4. Finding joint angles using video or motion capture is more blank than using a manual goniometer. I'll make this bigger. Yeah, so this is another one. I would either say, for this one, I would argue it's either objective, which is what Jody just put in. Yeah, objective or valid would be my 2 go-to ones. So reason being is if you're using a manual goniometer, that means you are manipulating the goniometer to measure the joint angle. Motion capture, if you yourself are doing it, that's going to insert bias or investigator error potentially. So objectivity is related to bias. So for this one, I'm just going to put objective or valid. This one I'll also add because we talked about that one too. Valid would also be a potential answer for this one because motion capture, it's based off of, I don't know if any of you have done analysis on this before, but you have kind of like a static marker set. And once you find out where your body is, you just track the motion using a cluster. And that relationship of the cluster to other clusters on your body those distances are supposed to be the same no matter where you're moving. And that's how you can quantify a joint angle. So it could be more valid because the camera is more sensitive to where you are in space. But yeah, objective or valid, I think, are two good answers for that one. Juan, can you clarify what you mean by your question? What is it? Like I thought objectivity or validity? Oh, the answer? Oh, like finding joint angles using motion capture is more erroneous than using a goniometer? Or did you mean like investigator error? Investigator error. Got it. If you're finding the joint angles using motion capture, that would I don't think investigator error fits in the blank very well, because that would be referencing that the motion capture is the investigator error, or that motion capture implies more investigator error than a manual goniometer, and it would be the other way around. Because investigator error could be due to bias, right? If you misread the goniometer, if you're inexperienced, like our previous example, and you didn't measure it correctly. So the way that the example is ordered, the reason why we have a motion capture is more objective or more valid than a manual goniometer is likely due to the fact that there is a possibility of investigator error, but investigator error makes the measurement less objective or less valid, if that makes sense. Yeah, okay, cool. All right, number 5. In a grouped frequency distribution, the blank size is determined by taking the difference between two adjacent upper bounds / lower bounds of a group. Yeah, carrots. Cool. We'll just say it's interval. Okay. This is one of those cases where interval doubles as two different types of definitions, I guess, right? Because interval size is in reference to a group frequency distribution where we're looking at what's the distance between one group and another, right? Which is, we calculate it by taking the difference between two adjacent upper or lower bounds. But interval also represents a type of data. So yeah, this interval is referring to the interval size, not interval data, just for clarification, unless anyone got confused. Yes. Okay. Number 6. Oh no, I'm gonna zoom out just a smidge. That way I don't cut off the word bank. Number 6, a researcher not treating subjects the same is an example of blank and affects blank validity. Anyone else feel like they want to chime in? Yes. Cool. Yes, so this would be an example of investigator error. And I can't spell investigator. Yep. It's Monday. Oh, this day's been wild. Okay. And it affects internal validity. Okay. So investigator error or investigator bias is usually due to error from the investigator or the person actually conducting the data collection. Right. So again, examples would be if they're inexperienced, if they misread something, if you misreport something by accident. So let's say you're in a spreadsheet and you're reading a questionnaire and you input the wrong value that somebody reported, say, as their height. Right. So those are types of investigator error. They're going to affect the internal validity of the study. And recall, internal validity is referring to like the study design itself. And if there are any components within that study design that are going to affect the outcome, such that the outcome is more related to the errors that were made and less to the intervention that was applied. Cool. All right. I don't see any questions popping up, so we'll keep going. For number 7, the blank can be used to compare the variability of data from different units of measurement. Key part, compare variability. If any of you have reviewed your feedback on activity 2, this hopefully you remembered. Yes, COV. Okay. So several of you, if you recall on activity 2, you guys had like squat 1RM, bench 1RM, what was it, like swim time, GPA, height, weight, that type of thing. And I had asked you which variable has the greatest degree of variability. And the follow-up question was, how did you determine which variable had the most variability? It should have been the coefficient of variation, because this is a type of standard score. Right? Remember, standard scores are values that we can calculate or use to evaluate things that either came from different samples or different populations, and or we can evaluate units of measurement that are not the same, okay, using the standard scores. So coefficient of variation or coefficient of variability, what that does is it puts all of your variability measures into a percentage. And because even if you had like a VO2 max versus a height versus a GPA versus a bench 1RM versus a squat 1RM, whatever your measures are, even though those have their own units of measurement, as soon as you put them into the coefficient of variation, you turn them into a percentage, and then you can compare all of your percentages. Right, so then whatever variable has the smallest percentage has the least variability, whichever percentage has, or whichever variable has the highest percentage has the highest variability. So that's like a little comment on activity 2, but yes. Coefficient of variation used to compare variability of data from different units of measurement. Okay, number 8. A researcher studying the effects of low cadence cycling on time trial performance for master athletes only had elite males volunteer for their study. This is a problem with, these are all great. I'm going to say the answer was external validity. Okay. Reason being is that our sample is elite males, but the target population is master athletes. So we got the elite part right, but a better or more representative sample of our population would have been including both males and females. Okay, so on this question, I also would probably accept sample or sampling, just because the sample is the thing that's wrong with the whole thing, right? But in terms of statistical inference, right, the external validity is where we have the issue, because the sample that we've collected does not, that their results are not going to entirely extend to the population that we're targeting. So we might say for elite males, you know, there's a certain effect that happens, like maybe their time trial performance goes up. I don't know, right? So if their trial performance goes up, and we extend that result to every type of master athlete who cycles, that's not really a nice picture, right? Our sample doesn't represent our population. So external validity. And then I think this is, oh, we have one more after this, but this one is like just answer greater than, less than, or equal to. In data that is normally distributed, the median is likely to be greater than, less than, or equal to the mean. Equal, 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 equal. Yeah. Now, I'm actually glad we're on this question though, because some of you in your activities were using this criteria to assess normality. And it'll be in your feedback if you did. But even though in like a perfectly normal distribution, we know the mean is equal to the median is equal to the mode. And even though that's a characteristic of a normal distribution, it's not kind of a reliable way that we can assess normality. We can get an idea of like where skewness might be, but you can imagine for like kurtosis, if we have positive kurtosis, that results in a high peak in the center. So our mean and our mode might still, and our median might all still be equal to each other in a sample that has positive kurtosis, for example. Skewness, usually you can get an idea with how the equalities change, but using that might not be the best way. It's not a valid way to assess normality. In the chat, yes, Z skew, Z curt, that's like the best way to assess normality. Some of you, if you've reviewed your feedback for activity 2, you maybe used a histogram independently, or you used the Shapiro-Wilk test independently. Usually for those two, those are the next 2 common ways that people will assess normality. With those though, you can't always tell what the actual distribution shape is unless you pair them with the Z skew and Z curt values. So with a histogram, usually it's pretty easy to see if you have skewed data because they'll, there will be an indication of a tail on some end. Kurtosis is a little bit harder to visualize through a histogram. So it's not always detected if you're solely going off of the histogram, in which case you would have to pair it with a Z skew or Z curt value, or Z curt value actually, if you're trying to detect kurtosis. Same goes with the Shapiro-Wilk test, right? You're given a p-value if you are accepting or rejecting the null hypothesis that your sample distribution is normally distributed. But it doesn't tell you how your sample, right? If you end up getting a p-value less than 0.05 and you can accept that you don't have a normally shaped distribution, how is it not normally shaped, right? In which case we pair it with the Z skew or Z curt, and then we can figure out if we have positive or negative skewness and or positive or negative kurtosis. Question, out of the 3 methods, identifying skewness is probably the best to find normality. Yeah, Z skew or Z curt, those are my go-to ones at least. But that's the kind of like the only way you can truly justify what type of skewness you have and what type of kurtosis you have, if there's any at all. Yeah. Cool. Oh, and just while we're on that, the criteria for those, remember, is that if your Z skew or Z curt value is within negative 1.96 or positive 1.96, then you have a normally distributed data, or your sample is relatively normally distributed. I feel like I had a thought and I wanted to say something, and now I can't remember what it is. It'll come to me later. Okay. Last one in the word bank example. We would calculate a blank when estimating a population percentile for a given raw score in a sample. Anybody who came to office hours today should be able to answer this one. Yeah, we do calculate a z-score. Oh, I just typed that in the participant section. I didn't want to do that. Here we go. Oh, dear God. Z-score. Okay. So z-scores we calculate using this formula, right? So we have a raw score of interest, the mean of our sample divided by standard deviation. We then can, after we get our z-score, we look it up on the z-table, and that gives us our percentile for that raw score. Okay. Exact percentiles are going to be using our cumulative frequency formula. That's what it's called. Cumulative frequency formula if you're working with like a simple frequency distribution or rank order distribution. I think the example I gave you guys in class, you had like a bunch of power data. So same thing goes. Remember, cumulative frequency is the number or the frequency of values that occurs at or below your raw score of interest. So in order to find the cumulative frequency, you would want to use a count if function that is inclusive of the raw score. And that was the dummy mistake that I made in the activity video that I emailed you guys about yesterday. The other exact percentile calculation is for grouped frequency distributions, and that's this complicated one here. So yeah. To address Juan's question in the chat, whenever it's an estimate, right? Oh yeah, z-score whenever it's an estimate. And that was the distinction actually. If you came to office hours, we talked about this today. There's a question on the activity 3 that asks you what the difference is between the exact and estimated percentile. And actually, I think it's the power data. Yeah, the power data. Okay, so an exact percentile does not take into account the shape of the distribution of your sample. A z-score or an estimated percentile does, right? Because the z table is based on the assumption that you have a normal distribution where 50% of your data lie above the mean and 50% of your data lie below the mean. In an exact percentile, that could happen, that could not happen. It depends if you have skewness or an extreme score on one side, and if that extreme score is significantly kind of changing where your mean is in your distribution. So yes, we use z-scores when we want to estimate. And then the probability that we get from that z-score is the area to the left of that score, which would be important if you were drawing your distribution or constructing your distribution. There were some examples of that in the Module 2 lecture. So if you haven't practiced any of those problems yet, I would recommend doing it because hands down, that will be a question on the test. You're welcome. Everyone's frantically writing down construction distribution. Oh, I know how it is. It's okay. Have I called you out? Maybe. Okay, but definitely know how to construct a distribution. What I mean by that is where you draw. I'll probably just give you a shape and then say, you know how we have like 0 or the mean in the center and then standard deviations on the outside. Each of those points on that distribution will be a letter. And then I'll give you a set of data, probably the mean and standard deviation. And then I'll ask you, you know, what area or between approximately which 2 letters would you shade to get what we're targeting here, or what percentile would exist in that shaded region, that type of thing. Oh. So it's important to remember the left area to the left, because if you want the area to the right or the area between 2 scores, you have to know how to manipulate the percentages a little bit. Okay, I'm gonna keep going. There's lots to do. There usually will be a section on the exam where you have conceptual scenarios. So I'll give you a research question or a study design setup. And then similar to your discussion one, based on that information, you have to pull out what the independent, dependent variables are, as well as what types of data those represent. So discussion one was useful. Okay. So I was going to jump straight to the answers, but you have the following research question. What is the effect of carbohydrate, caffeine, and carbohydrate plus caffeine mouth rinsing on intermittent running performance in collegiate male lacrosse athletes? So, what is the independent variable or variables if you think there are multiple? Yeah, I would agree with the chat. So I'm just going to put mouth rinsing solution or type of mouth rinsing solution. If we were to break this down into levels, level 1 might be carbohydrate, level 2 might be caffeine, level 3 could be carb and caffeine. Okay, so given that information, what type of data does the mouth rinsing solution represent? We have 4 options. Yeah, I love it when this happens. It is nominal data. Hopefully all those practice problems paid off, you guys. Okay, so it is nominal data because it is a category. We're sorting our sample right into carb, caffeine, and or carb and caffeine. Okay. So it is a categorical variable. What about the dependent variable? Yep, performance or running performance if we want to be more specific. Because that's the variable that we are actually measuring. How we are measuring it, not really sure, but performance is generally what the outcome is that we're interested in. And then let's say we wanted running performance to be measured in seconds. So we have people who run a certain distance. What type of data would that represent? Ratio. Abso-freaking-lutely. Cool. Okay. This is another common question that I'll ask you guys. Honestly, this entire section, just expect that to show up the rest of the semester. So, yeah. So question 13 is going to ask what hypothesis would be statistically tested. So let's focus on the answer to that first. Yeah, null. The null hypothesis. The null hypothesis is always the one tested. The hoe! Yeah. I love saying that. Oh no. Okay. Yes, the null hypothesis is the one that's always statistically tested. Same. And if we were to write that out in terms of the variables we have, does anyone want to try typing that in the chat?
Could be like the different types of mouth solutions don't have an effect on running performance. No signal.
Mm-hmm. Yep. Yeah, Jody, that would be correct. Yes, Juan. Yeah. So, in simple terms, type of mouth rinsing solution has no significant effect on running performance. Oops. Here we go. You could also type it as there's no significant difference, or maybe no significant differences between the means of running performance based on mouth rinsing solution. We get a little bit more into this wording when we go to t-tests. But another way you could write it is that running performance. Oh my God, my cats are fighting, sorry. Running performance is, or the means of carb running performance, caffeine running performance, and carb and caffeine running performance are equal to each other. I'm not going to type that out, that's too much, but yeah. How specific? For the null, as long as you get the point across that there is no effect, sometimes it might be that you're looking at the relationship between two variables. So no effect, no relationship, no significant difference. As long as you have that component, as well as the variables that are being tested, then you're fine. Some people like to write, the IV has no effect on the DV. What is the IV and what is the EV? So if you're, or DV. So if you're writing something like that, just make sure you have the variables inserted into the IV DV section. Yeah. Cool. The other thing would just be to pay attention to the wording, right? So like this one, I said, what is the effect? Null hypothesis would say no effect. If I was saying, what's the relation, or what is the relationship between height and body mass? Then the null hypothesis would say that there's no relationship. So paying attention to the use of word of effect and relationship would also be important. Neil asked a question, what if the research hypothesis wanted to test that there's no relationship between two variables? Typically, that's not the case. Because the null hypothesis will always say no relationship or no effect. In which case, in like research, if we were reading that, the researchers would say like, we hypothesize that there would be no relationship. They just state what their hypothesis is, and it's kind of known, like the null says no relationship, no effect. The opposite of that, or a mutually exclusive statement to that, would be the research hypothesis. So I don't know if that answers your question, but the null should always say no relationship, no effect. Yeah. Number 14, if the results show there is a significant difference between mouth rinsing solutions with a P less than 0.01, what does that mean? Reject the null. Yeah. I don't know why I have that many lines there. But reject the null. And yes, there was a significant effect. So in that case, we could restate the research hypothesis, which would say that mouth rinsing solution, or the type of mouth rinsing solution, if we want to use good English, has no sig effect on running performance. Juan had a question, what about not normally distributed? It depends on what the p-value is looking at. So our p-value says there's a significant difference, and the p-value is just 0.01. If we were looking at a p-value for a Shapiro-Wilk test, that's when you're addressing the distribution. So if you guys recall, I think it was last week, I said there's a lot of null hypotheses to keep track of. There's the null hypothesis for the main effect of the test, which is more or less what we're kind of looking at in this example. But you also have null hypotheses for like the Shapiro-Wilk test. You have a null hypothesis for a confidence interval, right? If you're 95% confident, or the null hypothesis would say, whatever your level of confidence percent is, that the mean lies between two values, right? So, yeah. This class is fun. Insert crying. Okay. Any questions on this one? These are all great questions you guys are asking too, by the way. So keep them coming. All right, let's do our written calculations then. I usually will break the test up into sections. So you'll have one that's more solely based on terminology, one that's based on conceptual stuff, and one that's based on Excel SPSS stuff. So written calculations, this will be the area where you might want to show your work. The Excel SPSS calculations is, you can still show your work in those parts, but that'll be the area where it's like you just type a number in or you type your interpretation of the result that you got. So that's the distinction between these two sections. Given this set of data, what type of distribution is shown? I see it grouped. Yeah. I wonder what gave it away. The groups. Okay. Oh, cats. Chill out. Okay. I don't know if you guys can hear them fighting. Sorry. I'm going to copy this table and paste it into Excel, which means that I temporarily need to get rid of some things on my screen. Oh, that's big. Oh, that's why. Okay. I'm just going to make this 12. That should make 100 more bearable. There we go. Okay. So I'm going to paste my data straight from Word. And then instead of keeping these clumped together, oh no. Instead of keeping these clumped together, I'm just going to separate them. So I can see my pattern here. And then I can see this other pattern. And then everything's formatted appropriately. I'm gonna get rid of the borders because it's messing with my OCD. And then we have our frequency column. And if some of you are looking to the question ahead over here, what percentile does a value of 27.2 have? I'm gonna move this down where we're looking at an exact as well as an estimated. That way we get practice doing both. Oops. Okay, so let's do the exact one first, since we've got our group frequency distribution set up already. My raw score X is going to be 27.2, and I'll put exact up here so that we can keep track of things. Okay. And those are a little too small. Sorry. I have formatting issues. I can't I can't deal with it when I'm looking at it. Okay. What do we need to calculate an exact percentile given this raw score of interest? Or is there a formula we should be following, et cetera, et cetera? I can't choose the right symbol. Let me take you back to your equation list. Remember, this one is an exact percentile for group frequency distribution. This one is for when we have either a simple frequency distribution or we've got just a mass of data. Okay. If we specifically have stuff grouped, then this is the one we want to follow. So I'll scroll back. Actually, I'll keep this up so we can reference where numbers are coming from. Move that over here. Okay, so we'll start with equals. I'll make this a little bit bigger so that you guys don't have to squint. Whee. Okay, so we've got equals. And then if you remember, when you put this one into Excel, you do 4 parentheses. You can keep track of the colors if you can see color. But in the top, we've got X, or our raw score, so we can just reference X, minus the lower bound. Okay, so you can put in the chat what you think the lower bound would be. 26. Yep. So the lower bound is the lower bound value in which, or lower bound of the group in which a raw score exists, right? So 27.2 is between 26 and 27.99. Therefore, our lower bound would be 26. Close the parentheses because that's our numerator for this little section here. Then we divide by the interval size. What's the interval size? I see a 2. Yeah. Remember, interval size, we take the difference between 2 adjacent lower bounds or upper bounds. Okay, close the parentheses on that one. Okay, close. There we go. Right, because that's going to close off this square bracketed section. And then we multiply by the frequency. So what's F? 10. Yep. So the frequency of the group in which our raw score resides in. And then we add the cumulative frequency, which would be I see a 59. I'm not exactly sure if that is the actual value, but what we could have done a cumulative frequency column before we started doing all of this, or I'm going to use a count, or not a count, a sum. So I didn't do this in your guys' activity. This is a bonus, if you will. Because remember, the cumulative frequency is the sum of all the frequencies preceding the group that you're in, or going towards the direction of the worst value. So in this case, vertical jump is like the higher the jump is, the better your score. So I'm going to count all of the frequencies below the group that I'm in, which would just be the sum of all of these frequencies. So did it already count some? Yeah, watch the formula bar because I think it's cutting off over here. So I'm going to do sum, and then I can just highlight that frequency area. Actually, I don't need this one really. So that cumulative frequency would end up closing off the top, or my numerator, which would be associated with the red parentheses. And then I would divide by my sample size, which again, I can do a sum of all of my frequencies, and that should give me my total sample size. And then I multiply all that by 100 to make it into a percent. I'm just pausing so that people can make sure they have everything typed in correctly. You can put a thumbs up in the chat if I can click enter. Or user participant reactions, whichever one is easier. Cool. I only got 3 thumbs out of 16, so. Okay, there's some more. I feel better now. All right. So you guys probably got 77. The other way we could have done this, I'll just show really quickly, is the way that we did it in the activity, where we had a cumulative frequency column, and you start counting at the worst value, right? So cumulative frequency at the worst or at the bottom is just going to be equal to the frequency of the worst group. And then we can add, oh my God. We could add the frequency of the next group and then just copy this. So if you did it that way and you wanted to calculate your exact percentile, I'm just repeating this equation here. We've got 4 parentheses, x minus the lower bound divided by the interval size times the frequency plus cumulative frequency below. Oh, so to answer your question, Vanessa, you were very close. It would be 71. You had to go one more group. Okay. So that's this part plus C divided by the sample size of 100 times 100. 77. Yay! Okay, so 2 different ways. I'll double click on this one so you can see there are practice problems for these last week's lecture. So if this process didn't make sense, I would recommend going back to look at those. All right, we also can do an estimated percentile. So I'll just put EST for this one. Bold and do that. Okay, for an estimated percentile, what are we calculating? Chat. We do need a standard deviation. We need a z-score. Okay, what I was looking for was z-score. Let's put x, that's our raw score. And we said that was 27.2. Right? To calculate a z-score, what do we need? The raw score, obviously. Mean and standard deviation. Okay, so I'm gonna put the mean, standard deviation, that'll give us our z, and then we can look that value up in the table to get our estimated percentile. Okay, so for the mean, you all should be familiar with that one. Oh, shoot. I just realized we cannot do it for this example because the data are not spread out the right way. But if we had a set of data that looked like this, we could definitely use the estimated percentile calculation. I just didn't register. This has to be listed out in an ordered list, and we don't have the actual exact values that exist in each of these groups. So, haha, just kidding. Grouped, no estimated, correct? Yes. I'm glad I made that mistake. Now you guys know. If it's set up as a group frequency distribution, the only percentile you can calculate is the exact one. Yes. Oh, lovely. Oh yeah, so I can explain why. For the grouped frequency distribution, the only information we have is the range of each group and how many people in our data set fell into that group. So any value between 12 and 13.99 can be assumed by either of these two values. So it could be 12.01, it could be 13.57. Yeah. So because we don't actually have the exact data points, we can't figure out what the estimated percentile is because we can't calculate the mean of the group. Well, I'm glad I made that mistake. Sometimes good things come from being dumb, so. Yay. Yes. Oh, I'm sorry. People watching recording. Question was, so we need to use the raw data. Yes. If you're doing an estimated percentile, you have to have the raw data in order to calculate the mean and standard deviation. Unless I give you the mean and standard deviation and then you just plug and chug. But grouped frequency distribution, you can only do an exact percentile. So we can go back to this. I'll take that out. And our exact percentile would be 77% or 77th percentile. For these calculation ones, I would also keep an eye on the decimal places that you report or that need to be reported. On your activity this last week, I specified like, oh, to the second decimal place or to the first decimal place. I should have done it better. I did it on my answer key and someone pointed out that I needed to do it on the actual answer sheet too. But pay attention to decimal places on the exam because usually those questions I have like a baby answer bank. And then if your answer matches any of the ones in the answer bank, it'll count it as correct. But if you rounded, like say I wanted to the nearest 10th and you rounded to the nearest whole, it'll automatically count your answer as wrong. Which when I scroll through, usually I can catch those, but sometimes if I miss them, then you just got it wrong because you rounded your answer. So just keep an eye on decimal places that you're supposed to report for those ones. Same thing would go for the SPSS and Excel calculations that we'll do in a second. Okay. If the answer is 12, oh, turkeys. Segue. I have turkeys who live in my backyard, and they all had babies, so they're little hatchlings are walking by. I got sidetracked. Sorry. Juan's question. If the answer is 12.46, but we got 12.45, it would be round or partial. Usually, I will put both answers, just in case people round differently. But my rule of thumb is that if you're at let's say the third decimal place in your example, 12.46, and the number after that was 5 or greater, you round up. If it's 4 or lower, you round down. Yeah. Cool. Also, the family of turkeys is called the gobbles. We tell them to hide during Thanksgiving. Anyways, that got dark really fast. Okay, so I will give you, I told you guys you have to be able to read graphs. So this would be an example of reading a graph or a frequency distribution. So what is the median of the data set shown in the figure? We're also going to be calculating the mean, but before we can do that, what should we do to this? Put it in Excel. When all else fails, put it in Excel. I gotta move some stuff. Hold on. All right. I don't know why this is formatted so huge. Lord, oh Lord. Okay. And just because I have issues, just gonna make those smaller. Okay. So I'm just gonna paste the picture in here so I don't have to go between different windows. But get rid of the empty space. Oh no. Okay, so this is our frequency distribution. We have number of squats noted here. Okay, so that's the variable that we're interested in, number of squats. Right, and then we have our actual squat number that people were able to achieve on the x-axis, the frequency of people who were able to achieve those numbers of squats on the y. So if we go through here, nobody had 11 squats, so we can just skip that. One person had 12 squats. So our first value in our distribution would be 12. Nobody had 13. One person had 14. No one had 15. One person had 16 and 17. Two people had 18, 19, 20, and 21. So 18, 18, 19, 19, 20, 20, 21, 21, 3 people had 22 and 23. Kind of see where I'm going with this? Okay. 5 people had 24. 1, 2, 3, 4, 5. 6 people had 25 squats. 1, 2, 3, 4, 5, 6. 6 people also had 26 squats. 1, 2, 3, 4. 2, 3, 4, 5, 6. 4 people had 27 squats. There. And then 2 people had 28 squats. Right? So similar way that we build a frequency distribution in the respect that we count how many people got the same number and then plot it, we can take that information out and kind of disseminate it into a list of data. And then the questions on here were to find the median and the mean. So we do have a function that can calculate the median, and we have a function that can calculate the mean. Each of them painstakingly being the actual function we're interested in. So to get the median, we do equal median. And we can put in our data. And I'll slide this over just a little bit so you can see. Okay, mean and or median and the range. For the mean, it's average and the range of data. And that would give us the mean. Okay. I want to change this to 2 decimal places just so I'm not bothered by it. And then move stuff around. The median that we would report would be 24. That's the middle value in our data set. And the mean, or the average, would be 22.93. Again, on answers like this, I usually will ask for a certain number of decimal places. So. Based on the shape in the chat, is it positively skewed, negatively skewed, or relatively normal? Got negative, negative, negative. Yeah, negatively skewed. Reason being is that our tail extends below where the mean is in our distribution. Okay. How do you know visually? I just answered that. Okay, so I'm just gonna put tail is to the left. That would suffice. Based on distribution shape calculations, we could do a couple things for that. We could put this into SPSS to get our skewness and kurtosis values, or we can calculate it in Excel. I'm just going to do it in Excel since we have it open. So you'll recall sample skew, SE skew, and we use those two to get Z skew. Z skew is actually the value that we evaluate in comparison to like the 1.96 value. And then sample curt, SE curt, and Z curt for our kurtosis. Remember in SPSS, if you're using either the frequencies analysis or the explore analysis to get your skewness and kurtosis values, that it will give you the sample and the standard error, right? Or sample skew curt and the standard error of skew and curt, but it won't give you the Z-score. So that was yeah, it's sad. There were several, what is it called? Activity 2 papers that I graded where I asked you guys, like, provide me this list of descriptive statistics, and some of you copied and pasted directly from SPSS, but forgot to calculate the Z skew and Z curt values. So if you want to use SPSS, you can, if like you don't remember what the equations are for this, But just remember, z-skew is sample skew divided by standard error, and z-curt is sample curt divided by standard error curt. And you can still copy and paste your output table into Excel and then just insert a row to do your calculations, whatever works, but just don't forget that step if you're using SPSS. Okay, so for sample skewness, the function in Excel is just equals skew. And then we input our range of data. Okay. Standard error, I give you guys this equation in your equation box. So it's this one. Should make sense because sample skew divided by skew and curt give it away. But this would be equals to the square root of 6 divided by n, or the total number of values we have in our sample. So we can use the count function for that one. Again, it's probably easiest if you follow the function bar up here. But square root function, parentheses, 6 divided by sample size, which we find by using the count function. And then highlight our entire range of data. And then z-skew would be our sample skewness divided by the standard error of skewness. I'm gonna zoom in. I realize it's kind of small. Okay, so again, sample skewness is equal skew, insert the range. Standard error of skewness is the square root of 6 divided by the sample size. And then z-skew is just the sample skewness divided by standard error. Okay. So based on our visual assessment, we said it was negatively skewed. We can confirm it is in fact negatively skewed because negative 2.65 is less than negative 1.96. We would do kurtosis in a similar way. So equals curt. Insert your range of data. That'll give us our sample kurtosis. Standard error is going to be the square root of 24 divided by the sample size. So again, we can use the count function to find the sample size. And then I'll leave that up, but z-curt would be sample kurtosis divided by standard error. So we just do cell references. And then in this example, we do not have any kurtosis. So if I go back to this one, hello, there we go. How do you know based on distribution shape calculations? Okay. I'm just gonna put in parentheses my distribution shape again is negative skewness, no kurtosis, or no curt, okay? I know this because z-skew is, which I calculated as negative 2.66, okay? That value is less than negative 1.96. And z-curt, which I calculated as 0.76. Z-curt is, I'm gonna put between negative 1.96 and positive 1.96. Oh yeah, Lori Joe, I think I answered that question earlier. So even though mean equals median equals mode is a characteristic of a normal distribution, it's not a valid way of assessing shape. So in this one, yeah, in this one, distribution shape calculations are going, just think of those as z-skew or z-curt. I could ask you guys to, like, if I give you a raw set of data and I ask you to analyze what the distribution shape is similar to activity 2, you could do it a couple of ways, right? I would confirm using z-skew and z-curt, but if you like to visualize or double check your answers with graphs, you can always make a histogram. If you like to double check with a Shapiro-Wilk test, you can. Just remember that the Shapiro-Wilk test is really sensitive to differences. So if you had a z-curt value of negative 1.6, it would think, oh, that value is really close to negative 1.96, which is our 95% level confidence alpha z-score, right? So sometimes when you have values that are really close to not making the 1.96 criteria, the Shapiro-Wilk test will say, nope, we're not normal, when in fact those z-skew and curt values would say that you do have a normal distribution. So if all else fails, just use your z-scores. In terms of conceptual information, if I asked you, what are the 3 ways you can assess normality? Then you would want to say like Shapiro-Wilk test, z-skew, z-curt, and you have an array of plots to choose from. Histograms are kind of the most common one, but there's also density plots that we covered in one of the practice videos for activity 2. You also have box plots that could also be used, because the whiskers usually kind of give you a good estimate of what the shape looks like. You don't get the normal curve over top of it, but they still give you an idea. Okay. Questions? Tie. All right. I've indicated that kin 263 is our next data set for questions 20 through 23. First question is, what is the exact percentile for someone with a Planck time of 151 seconds? So I'll put exact percentile over here, show that we don't get confused. And then what would I be using as my formula? Yeah, cumulative frequency. So this is the one where you could split it up and say cumulative frequency, sample size, percentile, or you can combine them into one formula. Either way should work. Just be careful with your parentheses. Okay, so cumulative frequency, we're going to use what function? Or if we want to know the number of values that are at or below than our criteria of X. Count if, right? I want to count the number of values that exist in my Planck time range, since that's the variable I specified. Okay, and I want to count values that are Planck time. Let's assume a shorter Planck time, not that good. Longer Planck time, good. Okay, so we want values that are at or worse than. So in this case, it'd be less than or equal to. And our X, which it's hidden right now, and that's kind of rude. So I'm just gonna click my up arrow, because you can see this little red box popped up back here. So that'll reference my X value. That will give me my cumulative frequency at or below than 151 seconds. So 61. And then my sample size is everybody who performed the Plancks. So I could just do a count function to find my sample size. It looks like we have 93 people. And then my exact percentile would just be the cumulative frequency, 61, divided by my sample size, which again, it covered it, but it would be the reference next to n. Okay. We can multiply that by 100 if we feel like it. So in this example, the exact percentile would be, oh no, here, that's what I wanted, 65.59. Again, for these ones, I would tell you how many decimals to round to. So review the, yes, the cumulative frequency, this one. So cumulative frequency, remember, is the frequency of values that occur at or worse than your raw score of interest. So I'm going to use a count if function because that allows me to say in this range of data, how many values meet a given criteria. So I've identified my range of data as all of my Planck times. And then I want values that are worse than or equal to, in this case, it's less than or equal to the reference for my raw score, which is hidden back here. Because Excel is dumb, but did that help? Yeah, cool. Next question, how many people can bench press between 110% and 119.9% of their body weight? How might we find that? In this case, we have an X1 and an X2, 110 and 119.9. Count ifs, right? If a function didn't come to mind, remember, if all else fails, you could always filter your data and then sort your values, like your Planck values. And then it would take more time, but you could go between 110 and 119 and count how many people. We could also use a count ifs function, right? Which is going to ask us to specify a range and a criteria. In this case, we would want to be inclusive of 110. Usually I would say inclusive or exclusive on the exam. I think I usually don't, I leave it out on here so that I remember to mention that I will specify on the exam. So there's that. But we want values that are greater than or equal to 110. So greater than, equal to, and 110. That's our first set of criteria. Our second set of criteria will apply to the same range of data, so D2 to D94. And that will be for our X2 value, for values that are less than or equal to and 119. Oh my God, you're right. The criteria is bench press. Thank you for catching that. I was obsessed with the Planck times, apparently. Did it switch it? Oh. Easy fix. Cool. So then we would have 34 people, and that would be our answer. Okay, so again, count if, like we use for cumulative frequencies, will give you the number of values that are within a range that meet one criteria. Count ifs will give you the number of values within a specified range that meet more than one criteria. These are why I ask you guys these questions on the activities. There is a method to the madness. Okay. Show the function one more time. Sure. Okay, so count ifs. Your first range of data, which is our bench press. We want values that are greater than or equal to our smaller value, right, which is 110. That's our first criteria. And then our second criteria applies to the same range. And we want values that are less than or equal to that upper or higher value of 119.9. Yes. Oh, I see what you're saying. So for people watching recording, we wanted to make sure if we include the upper bound. So like I said, for these questions, usually I will tell you include upper or lower. When you're building a grouped frequency distribution, the rule of thumb is that you exclude the upper bound, especially if values are repeated twice. So we already had an example of this. Let's say instead of 13.99, I put 14. Your frequency would then be inclusive of the lower bound, but exclusive of the upper bound, right? Because 14 is listed twice. Inclusive meaning less than or equal to, exclusive meaning greater than or less than, yeah. So that's a good callback question. But yeah, cool. And we only need to put less than or equal to at the last data value for grouped. Yeah, only inclusive of the last data value for group frequency because that value is not repeated twice. Good questions. Okay. Which class measurement has the most variability? What function would we use to calculate this, or what measurement? COV. Okay. What? No. COV. There we go. Okay. This is another formula that I've included on your, here we go, right here. Standard deviation divided by the mean. Okay, so we can calculate this actually pretty quickly, where we just say equals STDEV. And then I'm in my push-ups, so I'll start there. I select my range of my push-up data, divided by the mean or average, again, of my push-up data. And then I can multiply that quotient by 100 to get my percentage. If it makes you feel more comfortable and you don't like putting a bunch of formulas in the same, or equations or functions in the same cell, you could calculate the standard deviation and the mean separately, and then use references to your standard deviation cell divided by the cell reference to your average cell, multiply by 100, that would also work. Again, I don't care how you get to your answer as long as you get to the answer. Okay, so if we copied this across the other variables and we evaluated the percentage, go ahead and put in the chat which one has the greatest variability. I see a push-ups, yeah, right? Because it has the highest percentage. Okay, so for this one, we'll say push-ups. Okay. All right. Assuming the data is normally distributed, what is the probability that a random person from this sample would be able to run between blank and blank minutes? So the first two random mile times I'm going to use in this example. So anybody put a mile time in the chat. Yeah, any value between 7.6 and 12.6. So we have 11. I need one more number. 14. Oh, between 7.6 and 12.6. Sorry. 8.3, that works. Okay. That's all good. Okay, so let's say x1 is 8.3, x2 is going to be 11. And actually, I'm going to do it this way. No, this is fine. Okay. So I'm assuming data are normally distributed. I've also indicated that I'm looking for a probability. Does anybody know what I'm trying to ask here? Or what we're looking for? The z-score? Yeah, and what does the z-score tell us? Estimated percentile, booyah. Okay, so if you don't have your z-table open, go ahead and open it, or you can just watch mine, also fine, because we will need it. And I'll expand that. Okay, so over here, in order to get a z-score, we need a mean and we need a standard deviation. So I'm just gonna put a column here that says z, and then we'll have our percentiles that we calculate. Additionally, again, if you don't want to combine, you could put mean, standard deviation, z, then percentile. If that helps you check your boxes, spread them out. Okay. I don't care how you get it. I just want you to get the right answer. So the mean, again, is average. And we're looking at runtime. So I'll make sure I'm in the right column this time. Okay. We can find the average of our runtime. That's going to be the same no matter which x variable we are looking at. Same thing goes for the standard deviation. Okay. And then to get the z-scores for each of these, we do the raw score minus the mean. Make sure that's in parentheses so that your order of operations are correct. And then we'll divide by standard deviation. Similar process for our x2 variable. Oops. Parentheses, x minus the mean divided by standard deviation. Okay, so we get these two values. That would tell us which z-table to look up. I like to just use the decimal rounding thingy in Excel to tell me which z-score I'm looking up based on the second decimal place. That's one way you can eliminate some error. I think on the exam, I usually will round the other direction. So if somebody didn't round up to 0.26 and they kept 0.25, I still will record the probability just in case. But from this z-score, it's a -1, so we can look at the negative z-table. This is really small. I'm gonna go like this, so it's a little bit bigger. Okay, and we're looking up -2.26. So -2.2 is right here, this row. And then we would go to the column that has 6 in the 100th place. So 0.0119 would be our probability that someone would get at or worse than an 8.3. I already forgot what the number was. let's say 1.19. We'll write it as a percentage. That works too. Okay, so for these, if you put in an answer, like if I just ask you what's the probability that somebody was able to run a mile in 8.3 minutes, and you put 0.0119, that would be an acceptable answer, so as a decimal, or it would also be acceptable as a percentage, just for a note. I also want to find the percentile at 0.48. I don't know why I'm having trouble talking. So we would go to this row, right? 0.4, and then 8 for our 100th place. And that would be our percentile, right? Or the chance that we randomly selected a person in a normal distribution that had a mile time of 11. Oh my God, I keep forgetting, 68.44. Okay. And then from here, yes, okay. I had a thought, but then the thought went away. We can look at our question again. And we're looking for the probability that someone ran between these two numbers. So when we're looking at between, we have to take the difference between these two values. So we could say 68.44 minus this one. And then we should get the probability that someone ran between those two. Reason being, and I know we're out of time, I'm really sorry, but I can't find my drawing tool. There it is, draw. Okay, reason being is if we have, oh God, that's already bad. We have a normal distribution. This is where our mean is located. We saw we have a z-score of minus 2.26. So let's say that exists out here. And this is the probability for this guy. And then we also have our 68.84%, which lies at 0.48. So that's pretty close to where the mean would be. That would include the area over here, right? Again, to the left of the z you find. And the area we're interested in is people who ran between these two values. So the green space. Okay. That's why we subtract the blue area from the red area to get the green area. So that's what this is here. Sorry, that's kind of messy, but there we go. Okay. For squats, I'll keep recording. If you guys have to go, you can go. But I'll keep recording so that this part gets in the video. Are there any questions? If any of you are leaving, any final questions before you take off? Cool. If you have questions and you have to leave, just let me know. I answer emails, so there's that. To answer this one, I'll just type in 67.25. Okay. Again, you can either write it as a percentage or you can write it as a decimal. Okay. Question in the chat, how would you find the values above the part we didn't shade? Oh, so if I wanted to know somebody who could run faster or greater than 11, then I would do 100 minus 68.44. Extra credit quiz is this activity. So if you have the answers to this, then you should be able to answer the 10 random questions that are in the extra credit quiz. Yes. And then Lori Jo, are there any exam questions related to the activities? 100%. That's how I actually recommend people study for the exam, is to go back and do the activities again. Just so you make it, at least the practice part, so that you have the procedures down. That way, if I ask you a question and you're like, oh crap, how do I do that in Excel? You don't have to go back and watch the video while you're taking the test. But things like common functions, like how to calculate the minimum, maximum, how to calculate mean, standard deviation, how to combine cell references to create your own formula, or basic skills that you should be able to do. Filtering may come in handy. Yeah. So, yes. Cool. I'm going to go to squat, so anybody who wants to stay doesn't get kept here for too much longer. In evaluating the distribution of squat data, how would you describe it? So, how do we describe shape? Or what would we do? Skew and Kurt, right. So we would do the same thing: sample skew, SE skew, Z skew. This is kind of small. Try to blow it up a little bit. Whee! Okay. Right, and then we've got sample Kurt, SE Kurt, Z Kurt. I'll go through these ones a little bit faster just because we've already done an example of this, but we would use the squat data. The standard error is the square root of 6 divided by our sample size. Yes. And then Z skew would be sample skew divided by standard error. Sample Kurt. Whoops. There we go. SE Kurt, square root of 24 divided by sample size. If I'm going too fast, just go back through your procedures for this. I'm just going fast so we don't have to stay here forever. Okay. And then again, we would evaluate if we have met our normality based on the Z skew and Kurt values. So in this case, what do you guys think? What is our shape? Normal. Yeah. Yeah. Okay, so we would say data are relatively normally distributed. Reasons being that Z skew, which we calculated as 1.73, okay, is between, well, actually Z skew and Z Kurt, which was 0.07. So this would be R between negative 1.96 and positive 1.96. Okay, so when you're using z-scores to justify normality, make sure you include the z-score that you calculated as well as the criteria that you're using to evaluate normality. Okay. If we wanted to know for 25, which sport has the highest mean max knee flexion angle, We could filter our data by sport, which it looks like that's already the case. We can see our numbers are clumped together. And then we can say this is the mean for cycling, rowing, and running. And this is as simple as calculating the averages for the max knee flexion angle for each group. JK, pa! I was like, wait, why are they all the same? Oh dear God, it's Monday. For each sport, you would have to do, like, let's say I'm doing cycling, I would only highlight the data values under the label 1 for sport. Duh, that was a dummy move. For rowing, the range would be for data labels of 2 under the sport area. So that would be starting there to here. And then for my running column, it would be the averages for people with a data label of 3. Oops, overpassed. There to there. There we go. Okay, that looks more like it. So highest mean max knee flexion angle would be my rowing group. Any questions on that one? Okay. What is the sample standard deviation of experience for rowers? So standard deviation, I'm just gonna do this in line with the rowing column. And we're looking at experience. Rowers are a data value of 2. So I'll only take the standard deviation of experience values with a data label of 2. Right, and then my sample standard deviation, let's say, is 1.28. If you wanted to add the units, you can. Not necessary though. Questions on that one? Okay. Cool. All right, and then our last one is assuming the data are from samples that are representative of the population. So assuming they are normally distributed, estimate the percentile for a mountain runner that can squat 122% of his body weight. Okay, again, percentiles are looking at values at or worse than a particular score of interest. So if our raw score is 122, and we want percentile for a mountain runner, we are going to find the z-score. Sorry, I thought I had to yawn, but then my body decided not to. So I have mean, standard deviation, z. Particularly looking for a percentile of a mountain runner. So mountain runner should signal that we're only going to use the mountain runner group, which is data label of 3. So we can calculate the mean, which actually we already did. So I'm just going to reference this cell over here. My standard deviation, I know how to calculate that. And we're looking at squat data. So squat La-da-dee, from 3. My z is x minus the mean, divide by standard deviation, which is this column here. Oh my God, you're right. That is the mean of deflection. See, I'm glad I have you guys. This would be average. Squat. Boom. There we go. That should change it. Is that what you got? Oh, but it would be the mean of mountain runners only. Jesus, today has been such a long day. Dear God. Mean of mountain runners, this one to that one. Yeah. So mean of just the mountain runners. So squat data with the data label of 3. Same would go for standard deviation. And then we find the percentile of a mountain runner who can perform 122% or have a squat of 122% of his body weight. Z-score calculation shouldn't change. That's just raw score minus the mean divided by standard deviation. So then we can look that up on our Z table. It's a negative value, so we'll go to the -1. And we're looking for negative 0.56. So 0.5, that's in this row. 0.6 is in this column. So 28.77%. Or you could write 0.2877. Yes, I can show. Give me 1 second. Okay. If I had rephrased this question to ask, like estimate the percentile for a mountain runner that can squat 122% of his body weight or more, those would be one of those examples where you find the Z-score at the raw score of interest, which we did. And then if you were looking at the distribution, where the mean is in the center, let's see, we had a negative Z-score. So you can imagine your standard deviation tick marks. And then our Z was negative 0.5, so that would be between where the mean exists. Halfway between that and the first negative standard deviation. Z table gives us this area, right? And if I rephrase the question so that we want to know the percentile of someone who can lift 122% or more, that would be this area. In which case we would do 100 minus that percentage. Question in the chat. When we calculate a Z-score, the estimated Z-score is the calculated Z-score? Z-scores or Z-scores? The number from the table that you get is the probability that a value exists at or below that given Z-score, if that helps clarify. Okay, so that is that. I'm gonna, actually, are there any other questions before I stop recording? Okay.